All right, in this set of notes, we're going to be taking a look at extreme values of functions. So in this next section of notes in Chapter 4, we're going to be looking at applying the derivative. In Chapter 3, the chapter before this, in all those notes, we learned about how do we find the derivative of specific functions. We know how to find the derivative of polynomial functions, exponential functions, logarithmic functions, sine, cosine, all the trigonometric functions. Functions that are multiplied together using, so we have to use the product rule, the quotient rule, the chain rule, all of that. We know how to do that. Hopefully, we're experts at that because now we're going to move beyond how do you find the derivative to how do we apply the derivative. And one of those ways the derivative can be applied is by something called extreme values. Now, you've used extreme values in algebra before because basically extreme values are the max and min values. And now we're going to refer to them as absolute, or sometimes we'll talk about later, local extrema. Okay? So when we talk about absolute or local extrema, we're looking at max and min. So, application-wise, where can these be applied? Well, one thing is, like a pharmacist uses calculus to figure out how much medicine to give a person depending on their weight, their tolerance to a medicine. Obviously, a junkie is going to require a lot more medicine than somebody like me that's never takes ibuprofen, hardly ever. So my tolerance to medicine, if I ever go to the hospital, is going to be way lower, even though I might weigh more than a junkie that weighs 85 pounds or whatever. Also, what is the least expensive way to pipe oil from an offshore well? So if you're pumping oil through a pipe, you can use calculus to figure out, first of all, how much force is required, how much energy am I going to use, if I know that I want to pump this much in an hour, then how wide is or how big the diameter is my pipe going to have to be? So we'll be able to answer questions like that as we move throughout this chapter. So the first theorem, and the fact that it's theorem 1 is not important. I'm not going to test you, what is theorem 1? What I'm going to do is say, explain what the extreme value theorem is. So when you're talking about this with your friends, as you do on the weekends and your chats at night, I'm sure you do, talk about it as the extreme value theorem, not necessarily theorem 1. So if you have a function you know is continuous on a closed interval, very important that it's a closed interval, because if it's not closed, then the extreme value theorem cannot be applied. But if it's a closed interval, then you know that your function has both a maximum and a minimum value on that interval. It must have a maximum or minimum value. Now, maximum and minimum value can occur at either interior points, or they can occur at what are called endpoints. So here we have a closed interval, so these are dots that are circled in, and you notice that we have a maximum here and a minimum here. Now these are the interior points, so they are between your endpoints. But here, closed interval again, but the highest point on the graph occurs right there at your endpoint, and the lowest point on the graph occurs right there at this endpoint. And so then that is a case where your max and mins occur at endpoints. Here is a case where your minimum occurs at an endpoint, but your maximum occurs at an interior point. And this one, okay, as far as absolute extremas go, this is nothing. This is not important. But as far as absolute extrema goes on this graph, this is going to be your minimum that occurred at an interior point, and then your maximum occurred then at the endpoint. Okay, so when you're looking for absolute extremas, you want to check out both interior points and endpoints on the graph. And you know to include your endpoints if it's a closed interval. If it's not a closed interval, okay, so if you had from, let's say, closed at A to B and it's open, okay, this point right here, B, okay, cannot be an extrema. okay, because it does not include that b. So that means that endpoint cannot be an extrema. If we look at this example, there's all sorts of stuff going on here, but in this example, we're looking at what is a relative, or also called a local. So relative and local, they mean the same thing, extreme values. So looking at this, first of all, this point right here is a maximum. More specifically, it is a local maximum. By local, to tie these terms together, by local, what you're doing is relative to this point, there is no other point on the graph around it that is higher. Because these points get higher, get higher, get higher. They reach a maximum point, then they get lower. So relatively, this is the highest point. You know, if we look at a point here, relatively, yeah, this is the highest point here. But if you look left, there's a higher point there. So this cannot be a relative extrema. Down here, this, again, is a local minimum, because locally it's the smallest or the lowest point. Then if we look over here, this also is a local minimum, because locally it is the lowest point on the graph. However, choose green. This point right here is it's a local maximum, you know, as well, but at the same time it is absolute maximum, because it is the highest point overall. There is no other point on this graph that is higher than that, so that is an absolute maximum. And this point down here, which is an endpoint, this is an absolute minimum, because there's no value smaller than that anywhere on the entire graph. So you have to understand the difference between an absolute extrema and a local or relative extrema. Okay, because you're going to be asked to do and find both of them on certain graphs. Then finding these extreme values is this theorem too. Again, theorem's not important, but in finding the extreme values, you are finding what are called critical points. And critical points tell you a couple different things. Like, for example, a critical point will tell you when your slopes, the slopes of the tangent lines, are 0. So right at this point, you have a horizontal tangent line right here. You have a horizontal tangent line, and that is identified as a critical point because look at the definition. Okay, you find the derivative and set it equal to 0. That tells you where to find the horizontal tangent. And that's where your critical points occur. Now, critical points don't only occur where the derivative is 0, because critical points can also be your endpoints. So right down here, extreme values occur at critical points and endpoints. So I guess you wouldn't call a critical point an endpoint, because an endpoint's not critical in that it doesn't have a horizontal tangent there. Not all the time. Sometimes I guess it could. Technically it couldn't if it's not differentiable there. So yeah, no, you couldn't. So a critical point right here can never be an endpoint. Critical points are going to give you all of your horizontal tangents of where they occur. All right. But extreme values, you got to look at both critical points and endpoints like we talked about before. All right, so let's take a look at this one. Use analytic methods to find the extreme values of the function on the given interval. So we're only looking from -1 to 1, and you notice that this is closed because it's less than or equal to, less than or equal to. So first thing we want to do is find the critical points. That's the first thing we want to do. So we want to find where the derivative is equal to 0. In this case, I guess it's g prime of x equals 0. So we're going to go ahead and find the derivative. So that's going to be 4x minus 8. And then solve for x. So you get 4x is equal to 8. And then x is equal to 2. Now, here's something very important. All right. Does that fit in on this interval? No. So this critical point is not on the given interval. All right, so it cannot be looked at, and I'll do this in stripy pink, it cannot be looked at as a possible extreme value. What that means is, since there are no critical points found within this interval with this given function, it's the endpoints that make up both extreme values. Because we know that there has to be two of them. There has to be a maximum and a minimum. So now what we have to do is we have to look at the endpoints. And the endpoints occur at -1 and +1. And so we look at the value of -1, compare that to the value of 1, because these are the y values. So we want to compare these y values to see how high this one is versus how high this one is. And so you would have 2 plus 8 plus 9 is equal to 19. Here you would have 2 minus 8 plus 9 is equal to 3. So these right here, this point and that point, tells you how high up on your graph. Okay, so this goes all the way up to y equals 19, and this one goes all the way down to y equals 3. And so what that means is, if we just sketch a graph, -1, 1. So we're down here at 3. And this one is all the way up here at 19. So it doesn't matter what it does in between here. This is going to be the highest, and this is going to be the lowest. Okay, it might look, since it's, what is it? So it might look something like this. Okay, so that means, to sum up, our max occurs at the point -1, 19, and then our minimum occurs at the point 1, 3. So that would be where your maximum and minimum are going to occur, and that's what we had to find. Here's another one. Go ahead and try this one on your own. Pause the video, try it on your own. Again, if you're not pausing the video and trying these on your own, guys, you're not going to learn. So pause the video, try this on your own, then come back and see how you did. So the first thing we want to do when we're looking for extreme values is find the derivative and set it equal to 0. So we're going to find the derivative, which I found here. It's going to be 3/5 x to the -2/3. Set that equal to 0. Multiply each side. So what I did here is I multiplied this side by 5/3, and then I multiplied this side by 5/3, but 0 times 5/3 is 0 anyway. And you're left with just this, and 1 over x to the 2/3 to get rid of that negative. But no matter what you do, you notice this is on the bottom. Nothing, even if I plug 0 in here for x, okay, if I plug 0, it's undefined, it's not 0. And so what that means is this function is never 0. And so what that means, if it's never 0, that means that there are no critical points. So this graph never, ever, ever comes up and then back down, or it never, ever comes down and comes back up. So it's either always going up or always going down. All right. So what that means in the context of this problem is that we have to look at your endpoints. So again, like the last one, our endpoints are going to have both the maximum value and the minimum value. So let's look at those. You're going to compare f of -2 to f of 3 to see which one is higher than the other, which would imply that it's the maximum. So when you plug -2 into your function, that's going to be -2 to the 3/5, and then you're going to plug 3, so it's going to be 3 to the 3/5. You don't even need to get values. You can probably see here that no matter what, this is going to be a negative answer, but this is -1.516, and down here this is 1.933. All right, so then our final answer is this is going to be your minimum, and this is going to be your maximum. Okay, these are absolute extreme max and min values. So then we're going to say our maximum occurs at the point 3, 1.933, and then our minimum occurs at the point, -2, 1.516. That's where they occur. If you're not sure, now technically when they ask where they occur, it's probably safe just to answer x equals. Okay, but what I would do is just give the coordinate. You have the y value here anyway. Okay, but if it's like on the exam, if it's a no calculator and you have this, come on guys, there's nobody that I know that can compute -2 to the 3/5 or 3 to the 3/5 in their head. Okay, so they don't expect you to compute this in your head. They would expect you to think, well, when I compute this, I am going to get a negative because it's an odd exponent, and so that means that this is going to be my minimum. And so what you could do is just say, well, my minimum occurs at x equals -2, and then my maximum occurs at x equals 3. All right, so just keep that in mind. You could either do the coordinate, whereas if you have the y value, you need to find it anyway, just put it anyway, or the x value tells you where something occurs. And later on, when we apply a lot of this stuff even further and start answering problems, where something occurs is very important, because sometimes they ask you where it occurs versus what is the maximum value, something like that. Anyway, let's go ahead and try a different style of a problem. This one is going to be pretty tricky to graph on your own. But if we look at the graph, we can go ahead and graph it on a calculator and look at it. But let me go ahead and sketch that for you here. So here we have the function. This is what it looks like. It's just a straight line. Whoops. Just a straight line right here from -3 to +1. And then a straight line from +5 to +7. Then you would connect those. So you're looking for the max and min. So this problem is to show you that the max and mins can occur. Nice. The max and min can occur on intervals. So for example, the minimum here, it occurs on the interval from -2 to 1. And this is inclusive because this is inclusive. So what I have to do is I have to match this. And since this is inclusive, meaning less than or equal to, I have to put brackets. And then also the maximum is an interval, and it goes from 5 to 7. Okay, so that's to say that your max and mins can be more than a single value. And if it's a straight line like what we see here, then you have to include it as an interval. Okay, we have one more problem to do here. So let's take a look at it. So now we're identifying critical points on, this piecewise function, and we're going to be able to do this without a graph. So first of all, we have to identify the critical points first. All right, so first thing we want to do is set each one of these, the derivative of each one of these equal to 0. So let's say this is equation 1. So with equation 1, the derivative is going to be -2x minus 2. Set that equal to 0. -2x is equal to 2. And you would get x is equal to -1. So that is a critical point. And then if this is equation 2, makes up the other part of the graph, I have to look for critical points on here, and it's quadratic. Chances are pretty good that it's going to have one. This is -2x. The derivative is -2x plus 6 is equal to 0. And so -2x is equal to 6. And so x is equal to, this is -6, is equal to +3. And that's another critical point. So our critical points are 3 and -1. So possible extrema. Okay, I'm going to make a list of them here. You would have x equals -1, +3, but also you have to include endpoints, or in this case, where these two functions meet up. Because it could be like this, like boom, and then this one meets up like this, and then this point right here, okay, is a maximum. But if we don't include it as a possible extrema, then we'll never know. So another extrema is going to have to be 1. We have to include that because it's like an endpoint. It's where this one ends and this one begins. So technically it's an endpoint. It's a possible extrema. So look at both critical points and endpoints at possible extrema. Now what we can do is we can run a test. So just find all your y values. So f of negative 1, we'll do f of 1, then f of 3 to see which one's the highest and which one's the lowest y values. So with negative 1, it gets plugged into this function here. So then that's going to be, when we plug it in, it'll be negative 1 plus 2 plus 4 gives us 5. And then when we plug 1 in there, it gives us negative 1 minus 2 plus 4 gives us 1. And then when we plug 3 in there, it gives you negative 9 plus 18 plus or minus 4. That's equal to 5. So you can see that in this case, these 2 points right here, these 2 points are the same y value. So those are the highest y value because we've identified those as possible, the only possible extreme values. So that means our maximum occurs at both points negative 1, 5 and 3, 5. And then your minimum is not shared. It occurs at just 1, 1. Whoops, went right through that. See how good I am. There we go. That's better. Okay, so then they occur at those 2 points. So again, it can be shared, but this time it's not on an interval. It's 2 specific coordinates or 2 specific points. All right. So in this set of notes, okay, our goal is to find the extreme values of functions. And how do we do that? Good question. How do we find the absolute or the local minimum? Those are what we call possible extreme values. Is first of all, we have to identify your endpoints. Those are possible extreme values. And secondly, you have to identify your critical points, which when you find the first derivative, set it equal to 0. All right. Have any questions? Let me know in class. We can definitely go over these notes, any part of these notes again. Start the homework, and good luck.